Okay, so we're back ready to prove the onto part. And so we're going to look at side work. This is going to be a little different because it's a little more interesting, a little more intricate in understanding the side work here. But we're going to set up our side work because for onto functions, you should always, look at some side work first, okay, to see where you want to go. So remember, in this case, so I rewrote our function again in our domain and codomain. So we want to say for all, let's say x, y in our codomain, so in C cross D, there exists, let's call it RS, in A cross B, such that what do we want to happen? We want F of RS to equal XY. Okay, that's what we want. The reason why this is interesting is because, and again, this is our side work, so this is not part of our proof, but f of rs for us is going to be h of r, comma, g of s, and we want to make that equal to xy. Okay, and it seems challenging, but you may be thinking, yes, because I know we are all thinking, that, well, for the one-to-one portion, we used the fact that H and G were one-to-one. And so for the on-to, we may have to use the fact that H and G are on-to, which we will. So I'm actually just going to save time, go into the proof. But on Wednesday, yes, if you have any questions, you can see me or talk to me about anything in the notes. Okay? So we're just going to start our proof. So proof. Okay, and this is the on-to part. So this is still part of that lemma. I believe it was a lemma. Yeah, I think it's the lemma 5.12. Okay. And so again, I'm going to use the same XY point that I used in my side work. Okay, but here, and you can write this differently, but I'm going to write it how I wrote it in my notes. So I'm going to mention H and G before I start talking about something else. So since H from A to C is on to C, and G from B to D is on to D, that means, okay, for every X in C, there exists an N1. And did I call it that? Yeah. I'm just gonna go straight from my notes. An N sub 1 in A, such that H of N sub 1 equals X. Okay, and that's just from the definition of being onto, right? And so that's looking at the H function. And for all Y in D, there exists a Q sub 1 in B, such that, and I really could have used different letters, so hopefully the subscripts aren't confusing, such that G of Q sub 1 equals Y. Okay. All right, so go back over that if you don't understand what I just did. Well, let RS belong to A cross B, such that we're going to let R equal N sub 1 and S equals Q sub 1, okay? And note, N sub 1 and Q sub 1 are in A and B respectfully, so that's legal. Thus, F of the order pair RS equals F of N sub 1 comma Q sub 1, which equals H of N sub 1. So it's the ordered pair H N sub 1 comma G Q sub 1. And that equals XY. Hence, F is onto C cross D. Thus, And, oh, okay, I can keep that. Thus, F is a one-to-one correspondent or bijection. And therefore, A cross B is equivalent to C cross D. So definitely go back over this in the notes if it's not clear. I did it kind of quickly, but go back over it because hopefully it should make sense. Okay, so you can see, and it will be nice to put in your notes, the top of page 236 for examples of the lemma we just proved. Okay, so now we're going to do some definitions, and we're going to end this video on the definitions because there are some theorems and lemmas that I just want you to write down on your own. So this is going to be sort of the last part of this video. It's a few definitions that will definitely be important for now until the rest of the semester with these new sections. Okay, so for each natural number k, let n sub k be equal to the set of 1, 2, 3, all the way up until k. All right, so our first definition is going to be a set S is finite if and only if S equals the empty set or S is equivalent to n sub k for some k in the naturals. Okay, so a set, and sort of hopefully that makes sense. A set is finite if it doesn't contain anything, right? Because that's cardinality 0. Or if S is equal to n sub k. And so that's sort of the one-to-one correspondence that we talked about. All right. 2, a set S is infinite if and only if S is not a finite set. Okay, so if the set is not equal to the empty set, or if it's not equivalent to n sub k, then we say it's infinite. Okay. 3, so let S be a finite set if S is equivalent to n sub k for some natural number k, then two things we can say. A is S has cardinal number k, okay, or we say cardinality k. And so notation, we write S with 2 bars across the top equals k. So from now on, instead of doing the absolute value, you can use this symbol because this is what will show up in your book for cardinality. Okay. But note that depending upon what book you look at, you'll have different types of notation for the same thing. So we're just, for convenience and for convention and for you to be uniform, we'll just use the double bars for cardinality. So if S equals, so part B, if S equals the empty set, S has cardinal number 0. Or cardinality 0. Okay, and for that we write the cardinality of the empty set equals 0. Okay. So an example of this would be, let S equal the set containing T, 1/2, C, and 99. Well, that has cardinality, as we can see, 4, or that's the notation. And since S is equivalent to N sub 4. Okay. And remember, N sub 4 is the set containing 1, 2, 3, 4. So again, like from the beginning of my first video, it's making that one-to-one correspondence with the natural numbers. Okay. And so in other words, that means we can create a function that has a one-to-one correspondence between S and N sub 4. Okay. Just another note for the identity function. So the identity of N sub K. So of course, that's the domain of N sub K to N sub K. This, and it should be straightforward, is a one-to-one correspondence with cardinality K, of course, or you can use that notation. Okay. And so now in your notes, so I'm done with my part. In your notes, I want you to write, including the proofs of these 4 theorems or lemmas. And they're pretty short because, as you can, well, you kind of know in the book, their proofs are pretty short already. However, here it's more of the quality, not quantity. So the proof doesn't have to be long in order for it to have a lot of different concepts going on. So I want you to look at those 4, and this is the end of the video for Wednesday. And then by, hopefully, if not Tuesday, by Wednesday, I'll have the videos for Thursday. Okay, so listen to these videos while I'll send you out an email. But this is the end in order to be prepared to work on the homework for class on Wednesday.